Oh, I see a recording symbol again.
Perfect.
Okay, it's good.
Great.
All right, so to continue what I was saying, essentially, when we're talking about this uniform superposition case, we want to have an equal likelihood of measuring every possible quantum bit string. Sort of key word here is equal likelihood. So as an example, I guess going back to that 2-qubit circuit, we essentially want to make it such that our probability of measuring 0, 0 is equal to our probability of measuring 0, 1, which is equal to our probability of measuring 1, 0, which is equal to our probability of measuring 1, 1. If we were to draw that out on a nice little graph, it would look something like this. So these are our measurement outcomes. And then our probability is encoded on the y-axis. So essentially, we want to make it look like each of these probabilities, likelihoods, have the same value of 25%, right? And in this case, there's 4 different possible outcomes. And we want to have an equal likelihood of each of the 4 possible outcomes. So each has to have a likelihood of 1/4, 25%. So this is sort of our key motivation here in creating this uniform superposition. And now the question is, how can we actually use a quantum circuit to create and measure a uniform superposition? It turns out that the circuit which encodes a uniform superposition is the circuit here that has a Hadamard after. So if we initialize every one of our qubits to 0 and then apply a Hadamard after each of those 0 states, we will encode a uniform superposition, which we can measure over, and we do expect to get that sort of equal likelihood over all of the possible outcomes. So now let's work through the math and actually confirm this. This is sort of the really cool thing now about us knowing how to work through the math of these quantum circuits, is that we can go and calculate it out and test that it works without relying on Qiskit or some other simulator to do the computation for us. We can prove it to ourselves. So let's start off with the input state, which again, we just take our tensor product between 0 and 0. That's 1, 0, tensor 1, 0, which of course is 1 times 1, 0, 0 times 1, 0, which gives us 1, 0, 0, 0. Now, let's figure out what the value is of the operations that we're going to apply. Let's create a large single matrix, which encodes the full transformation of this circuit. And that's achieved by taking the tensor product between 2 Hadmards. So we have 1 over square root of 2, 1, 1, negative 1, tensor 1 over square root of 2, 1, 1, 1, negative 1. And that ultimately is equal to 1 over 2 times 1 times 1, 1, 1, negative 1, 1 times 1, 1, 1, negative 1, 1 times 1, 1 times 1, 1, 1, negative 1, which gives us this beefy matrix, which looks like this. So it's 1, 1, 1, negative 1, 1, 1, 1, negative 1. Oops, I dropped a negative 1 sign here. 1, 1, 1, negative 1. And then in this case, we flip our sign, so we get negative 1, 1, 1. And so to calculate the value of psi, state psi here, which represents the full state of our circuit, so the value of both of these qubits right before we perform our measurement, we can find that simply by multiplying our combined matrix of Hadmards by our full quantum state of our system at input. So 0 tensor 0, which is this product here. Now, what does that give us? Well, we notice, right, that these last 3 entries are 0, so we don't need to be concerned with any of the terms here. It's basically just pulling out this first column here. So we get that size actually just equal to 1/2, 1, 1, 1, 1, which is equal to 1/2, 1/2, 1/2, 1/2. And so now, what does this mean in terms of our actual probability amplitudes, right? So we said earlier that this first entry here is our probability of measuring 0, 0. The second one is the probability of measuring 0, 1. This third one is probability of measuring 1, 0. And this fourth entry here is the probability of measuring 1, 1. And each of these is equal to the value of the coefficient absolute value squared. So 1 over square, 1/2 squared, 1 over 1/2 squared, 1/2 square, and 1/2 square. And so what is that? 1/2 square is just 1/4, 1/4, 1/4, and 1/4, which is awesome, right? We see that we get the 25% likelihood of measuring each of the possible bit strings. So going back to our previous slide, we get that we do have a uniform superposition over measuring each of these possible states. And this is actually sort of a really cool trick that I wanted to emphasize more generally for quantum circuits. So in this case, we worked it out in the 2-qubit case, but you could easily see, right, how this could extend to more qubits. So if we had some n-dimensional circuit and we wanted to create a uniform superposition over all n of our qubits, all we would need to do is just apply a Hadamard to each of them, assuming they were all initialized to 0. Of course, if they were initialized to 1 or something, we would still get uniform superposition, but we would just get weird sort of phases introduced. But that's really cool. And so now you guys kind of have your first building block of quantum circuits, which is how to initialize your circuits to this uniform superposition. And it turns out that a lot of algorithms actually rely on you being able to initialize to these uniform superpositions. So moving on, the sort of last example I wanted to give in this lecture and the last kind of key discussion I wanted to have was talking about entangled states. So in this case, we're going to talk about how you can create those sort of maximally entangled states that we were talking about before. These are actually known as Bell states because they have to do with the famous Bell experiment. If you guys have some free time and are curious about sort of fundamental breakthroughs in quantum mechanics, I would highly recommend you look up Bell's experiment, which basically disproved the sort of Einstein-Podolsky-Rose paradox and like notions of hidden variable theory. So Einstein and a bunch of other really smart guys who weren't big fans of quantum mechanics thought that quantum mechanics could actually be explained by like underlying hidden variables. And this was kind of uncontested for a while. And then eventually this really smart physicist, Bell, he came up with an experiment called Bell's experiment, which partially disproved it. It's still to this day, I don't think hidden variable theory has been fully disproven, but people have created increasingly strong experiments building off of Bell's experiments to give further evidence that it might be wrong. But he essentially kind of disproved some concerns that people had with quantum mechanics theory and so forth. But I'm getting a bit off track. Let's stay on focus here and just talk about how we can think about creating entangled states in a quantum computer using a quantum circuit. So there are 4 different possible Bell states. They represent the Bell basis. They look like this. And so one kind of neat piece of intuition is in these two Bell states, your qubits are anti-correlated, whereas in these two Bell states, your qubits are positively correlated. And when I say that, what I mean is if in, for example, this first Bell state, you measure 0 for the value of your first qubit, you automatically know you're going to get 0 for the value of the second qubit. If you measure 1 for the value of the second qubit, you automatically know your state has collapsed to the first qubit. And furthermore, in these anti-correlated one, the reason we say it's anti-correlated is instead you know you're going to get a 1 or the opposite value on your second qubit, and so forth. If we are to draw out the probability amplitudes in this case, for this 2-qubit example, let's look, for example, at this first case here. Plot out the probabilities. Our goal in this case is to, for our measurement outcomes, essentially, instead of creating a uniform superposition over all states, we actually want a uniform superposition over the positively correlated states. So now instead of our probabilities being 1/4, they'll actually be 50%. So this is the example we'll be working to create. And actually, you guys in your Qiskit tutorial last weekend implemented a circuit which does this. It looks like this. You essentially apply a Hadamard followed by a CNOT. And so now we're just going to work through the math to see why exactly this works, and we're able to achieve these 50% probabilities on the 0, 0, and 1, 1 states. So again, we start off by calculating the value of our input state, 0, 0, and just remembering it from before. It's just this vector 1, 0, 0, 0. Now, in this case, we actually have 2 time steps to our circuit. We have this first time step in which we apply a Hadamard on the first qubit, and we can say we're applying an identity on the second qubit. So we'll call this time step 1. And then in this second time step, we're applying the CNOT. So let's go through and calculate these out. So in the first time step, T1, we're doing the Hadamard tensored with the identity. So that's 1 over square root 2, 1, 1, 1, negative 1, tensored with the identity, which is 1, 0, 0, 1. And essentially what this gives us is this beefy matrix that looks like 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, negative 1, 0, 0, negative 1. For the second time step, we are simply applying the CNOT, which we remember, right, is already a 4x4 matrix. We defined it earlier in class, and it looks like and so if we want to calculate the value of, or the state of our system right before measurement, state psi, all we're going to do, right, is we're going to, we write this out, we're going to apply our time step 2, multiply that by our time step 1, and multiply that by the input state psi. Now to actually do that out computation-wise, that corresponds to taking this first CNOT matrix, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, multiplying it by the second matrix here, so 1 over square root of 2, 1, 0, 0, 1, 1, 0, 0, 1, 1, negative 1, 0, 0, negative 1. Multiply that finally by this last vector, 1, 0, 0, 0. All right, so just to make things simple, I'll actually start by multiplying these two out first, right? Because we noticed that these last 3 values are 0. So we can just ignore the values of these entries. And so we get that this is equal to, again, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, times the value of this product here, which is simply just 1/2, 0, 1/2, 0. Now, if we do this matrix product out, what we'll see is when we multiply this column by this first row, the 1/2 will multiply by the 1. So we'll get 1/2 here. When we multiply the column by this row, we just have 0 being multiplied by 1. So everything just goes to 0. When we multiply this column by this row, again, the only 1 value here corresponds to the 0 term here. So we'll get 0 again. And then finally, if we multiply the column by this last row, we actually see that this one corresponds to this 1/2. And so we get 1/2. So now, if we think about this in terms of our probabilities of measurement, so I'm just going to copy this vector here onto the next slide so we can think about our final step of measurement. We have 1/2, 0, 0, 1/2, right? And we know that this tells us about the probability of measuring 0, 0. This tells us about the probability of measuring 0, 1. This tells us about the probability of measuring 1, 0. And this tells us about the probability of measuring 1, 1. And the actual probability, right, corresponds to the probability amplitude squared. So this is 1/2 squared. This would be 0 squared, 0 squared. Oh, I think I might have actually made a mistake. Yeah, I said this was 1/2 when this should have actually been square root of 2. Sorry for that error, you guys. This was a 1 over square root of 2, so my mistake. And so if we calculate this out, 1 over square root of 2 squared, that gives us 1/2. 0 squared is just 0. 0 squared is just 0. And 1 over square root of 2 squared is 1/2. And that gives us, right, our desired 50% probabilities on our states 0, 0, and 1, 1 that we showed in our initial plot before, right? So we were able to create this superposition. And it turns out that you can get these alternative anti-correlated or correlated versions by applying X and Z gates to your different qubits respectively. And we'll explore this a lot more when we actually get into super dense coding and quantum teleportation, which are quantum protocols which make use of these Bell states to sort of distribute information more efficiently and to teleport quantum information in the case of quantum teleportation. So I guess that was sort of the last thing I wanted to say. I know that today's lecture was a bit dense. We worked through a lot of math, a lot of new concepts here, both mathematical and conceptual. So it might have been a lot to process, but hopefully you guys will get a bit of practice through the homework in your lab and start to feel comfortable. Over the next few weeks, we'll be looking at different quantum algorithms, quantum protocols, which make use of the circuits that we've been talking about the past few weeks. To perform really, really cool computation for all different applications. Deutsch-Jozsa was sort of the first quantum algorithm to show some sort of quantum advantage to a classical algorithm. Quantum teleportation enables us to teleport quantum information, which is really cool. And then when we get into our more advanced quantum algorithms, Grover's algorithm gives us a really nice quantum speed up for the problem of database search, and quantum approximate optimization algorithms are a really cutting edge state-of-the-art research field in which you use a hybrid quantum classical system to do optimization. So these are some really exciting things to look forward to. And if you can sort of master this math either before or while we're going through these quantum algorithms, that would be super awesome and put you ahead of so many people trying to get into the field of quantum computing. This is really tough, but I think it's really rewarding if you guys can really master the art of mathematically representing quantum circuits. So thanks to all of you who sticked on. I know we went quite a bit over the 2-hour period. So I hope you guys have a great week and enjoy your labs. Thanks, Gabby, for also staying on and recording for